So previously in this topic, we've been looking at collecting data. What we're going to be looking at now is the process of storing data. Before I go any further, you need to be comfortable with converting denary to binary, binary to denary, and also denary, binary, hexadecimal. If you're not, I'm sure I've got some videos on my channel. I might try and see if I can put some in the description below to get you all caught up with that. So what do we mean by storing data? Well, we're basically saying, how is data stored on a device, let's say like an SSD, inside a computer? How's it processed by a computer, by like the CPU? Well, in its base form, excuse the pun, binary uses base 2, it's in machine code. Machine code is binary. That is how data is stored inside a computer. Now, the smallest amount of memory is going to be a bit, which would be like one binary number. Then you've got a nibble, which is 4 binary numbers. You then have, or should we say 4 bits? So 4 bits make a nibble. You then have a byte, which is 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Now, we're going to go into some slightly different territory now. What happens next is that you've got kilobytes. So, kilobytes. To get from a bit to a nibble, ooh, that's a really thick pen. Let me just make that slightly thinner. Thank you. To get from a bit to a nibble, as I said before, it's 4 bits. 4 bits make a nibble. From nibble to byte, or let's do from bit to byte. 8 bits. 8 bits make a byte, or 2 nibbles make a byte. From byte to kilobyte, we're dealing with 1024 bytes. So 1024 of these bytes will make 1 kilobyte. You may have learned previously about 1,000. We're dealing with 1024. We then have megabyte. That is, let's keep the colors going, 1024 kilobytes. So 1024 kilobytes make a megabyte. We then have gigabyte. So that should be, come on, let's keep it consistent, Nevin. Gigabyte, gigabyte. And again, that's 1024 megabytes this time. 1024 megabytes make 1 gigabyte. We then have terabyte. It's 1024 GB. We then have, yes, we're going even higher, PB, which stands for petabyte. That is 1024 terabytes. We then have, yes, we are going even higher. So let me just move this up and move this up and move this up. We then have exabyte. So I'm going to do EB. Exabyte, and that is 1024 petabytes. We then have zettabyte. That is 1024 exabytes. And the final one is yottabyte. And that is 1024 zettabytes. And there we go. If we want to convert something going upwards, we divide it by these numbers. If we want to convert it going downwards, we multiply it by these numbers. So if we want to convert, let's say 4 gigabytes and turn it into megabytes. How many megabytes is 4 gigabytes? Well, you've got to multiply it by 1024 and 4096 megabytes. So 4096 megabytes make 4 gigabytes. If you wanted to work out how many terabytes are in a petabyte, so let's imagine we've got 1,000 and let's say 1,105 terabytes. How many petabytes would that be? So we take 1,105 and we divide it by 1024 because we're going upwards. And that will give us 1.079 petabytes. So we're always dividing by 1024 or multiplying by 1024, apart from when we go from bit to byte or bit to nibble. So if we want to know how many bytes there are out of 16 bits, we're not going to divide it by 8. Sorry, 1024. We're dividing it by 8 because there's 8 bits per byte. So that means that we're going to have 2 bytes from 16 bits. So if you've got 16 bits down here, how many bytes does that give us? It's 2 bytes. 2 bytes make 16 bits. From bytes to kilobytes, we then start using 1024. So if I said how many, if we've got 1,000, let's say 11,000 bytes, how many kilobytes would that be? We take this number and we divide it by 1024 because we're going up, which will give us 10.74 kilobytes. Okay, so you do need to be able to list these off in order. For a lot of you who do computer science, this should be really easy. You just got 3 new ones to be focusing on. You also need to be able to do the calculations by 1024. So we're focusing on storing data inside a computer. So not only do we need to know how to calculate the storage, which we'll have a little bit more practice on in a bit, we also need to know how different files are stored. So let's have a look at how characters are stored and represented. I'm typing on my, like say Microsoft Word, I type in the letter A. You see it on your screen as the letter A, but behind the scenes, the computer stores it as a binary number. 0110001. Actually, I'm missing a 0. 4 zeros 1. This is so that the computer can actually store it in a format which is capable to do that, because computers can only store things as binary. So it has to turn it from this A into what we have right now, this binary number, and we call that, it stores it as an ASCII value. So every letter on your keyboard, every command on your keyboard, let's say tab, let's say spacebar, they all have an ASCII value. I'm not going to write out tab ASCII or spacebar ASCII because I don't know them. So let's say we decide to type in a capital A. That also gets turned into, you got it, an ASCII value. But it's going to be different. It's not going to be the same. It's going to be 01. So we've got 5 ones, 5 zeros, and a 1. So this would be capital A. This would be lowercase a. So let's imagine that we're now using capital B. See if you can work out yourself what capital B is going to be. Well, its ASCII value is going to be the same as capital A, but this is going to be a 1 and this is going to be a 0. Why? Well, if we put our placeholder values down, blah, 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 this adds up to something in 1. What's the next number after 1? 2. So that'll be a 1, that'll be a 0. So what would capital C be? Well, it'll be 0, 0, 1, 0, 0, 0, 0, 1, 1, which will add up to 3. D would be 4, so it'll be 1, 0, 0, and fill out the rest with etc, etc. So this is like a UK/American keyboard. ASCII is what's known as a character set. It allows us to type English letters from the English dictionary, but also numbers, symbols, etc. But it's quite limited, ASCII is. If I was to using an ASCII keyboard, well, ASCII character set, do like a smiley face, it wouldn't work. You'll just see this. So this keyboard doesn't always, but a lot of the time it is or was using the ASCII character set. That meant that people in different countries wouldn't be able to type. So what do we know about ASCII? Well, as I said, it's limited. It's limited because it only allowed 7 bits of data to be stored. So that basically means only 128 different characters. So different, unique characters. Now, what about people from Russia? What about people from Japan? What about people from China? What about emojis? Those sort of things. You can't live life without emojis. ASCII is old. It was developed in the 1960s. There was a move away from ASCII. So ASCII, they realized, was limited. So they created a different character set. This character set is called Unicode. And it's known as being a super version of ASCII, a superset of ASCII. And the aim of it is to include every character in the world. So it's up to 32 bits. So that's 1 million or over 1 million different characters. So this basically means that I can still use this keyboard for Unicode. It's fine. I can then just do ... smile, and the computer will recognize this and convert it into a smiley, an emoji, and in the back end it'll be stored as some binary. So Unicode is a character set as well. So you've got two different ways characters are stored and represented inside a computer. So when we mean stored, we mean stored on the hard drive, kept in the RAM, display, processed by the CPU, but also how they are displayed on your monitor. In the olden days, ASCII would be enough. So all of this is converted into machine code, which is binary in ASCII. However, it's limited because it's only 7 bits. Therefore, we made Unicode. Unicode came out in early 90s. It's a superset of ASCII, so it uses ASCII but builds on it. So let's actually finally look at the differences between the two. This is the ASCII table, where we do have, if you look at what really matters, it's going to be this column called char. So that column, that column, that column, that column. So these are all the things you can do. These things you don't really need to be aware of anymore. It basically allows Microsoft Word, for example, to format your text the way you want it to be. Like if you press a heading, or if whenever you start your text, it'll know where your cursor is going to be to begin with, whenever you press tab. So these are like keyboard controls. These are the characters, really, which we use heavily. Unicode, on the other hand, is far too big for me to represent that way. This is just a sample of Unicode. Look at all of these different characters. Beautiful, isn't it? But it goes on and on and on and on and on. I can't fit it all in. So what we have here is two different types of images. We've got what's known as vector graphics. Over here we've got something known as raster graphics. Have a quick look at the differences between them in terms of how they're made up. See if you can work it out yourself. Raster graphics are going to be things such as photos, high quality images, etc. Vector graphics, on the other hand, are basically like illustrations. Vector graphics are made up of shapes. So it's using basic shapes and lines combined together using like a mathematical formula. So the way these are put in, they're done via like a coordinates. If I wanted to then stretch this picture out, so let's imagine we want to make it larger and larger. What happens is it doesn't lose its quality. So it can be enlarged. Why? Because these formulas, which they're made up of, adjust automatically based on this, what you want. So it keeps a ratio. So it's kind of like vector, I suppose. You could give it an analogy that it is drawings with maths. That's what it is. So you can make it bigger, smaller, and it adjusts the shapes and the lines. So you would see vectors being used with logos, etc. Raster graphics, on the other hand, are made up of millions, well, not all the time millions, but let's change the word millions to, they're made up of pixels. These pixels form a grid, like a mosaic. The more you zoom into an image, the more those pixels are obvious. This basically means that it's very challenging to change the size once you get going. So you can't really resize. it takes up a lot of memory in your computer. Each pixel is given a color. So each pixel is given a color. For more pixels, for higher quality. So for more pixels, let me just move over. More quality, but takes up more storage. An example of raster graphics is known as a bitmap. So what we have here is a bitmap image. What we have here is a vector image. They're both examples, vector and raster, of how images are represented by a computer. So we've looked at how text is stored and represented. So we looked at ASCII and Unicode. We're now looking at how images are represented, and we're now going to look at how they're stored. Now here's the thing. We can actually have more bits per pixel. So one pixel doesn't equate to 1 bit. We could actually have a pixel, so a little dot like that. Let me zoom right in. So a little dot like this, which can have loads of bits in it. For more bits, for more colors could be kept in that pixel. So how does that break down? Let's imagine that we've got a pixel. And this pixel has 1 bit of storage. That basically means that we can only store 2 colors. So if I was to do our placeholder values, we can either store a 1 or we can store a 0. 2 different types of colors, a 1 or a 0. So normally that's going to be black or white. So 1-bit pixel would be either used for a black or white color. Let's imagine that we then had a 2-bit pixel. That's going to store us 4 colors. Why? Well, 1, 2, now. So we've got our placeholder values. Now we could have 0, 0, which would be black. So that's one combination. We could have 0, 1, which could represent red. That's 2 combinations. I'm just giving you examples here. 1, 0, it could be blue. So we say black, red, blue. We could have, so that's 1, 2, 3, we have 1, 1, which could potentially be green. By the way, these aren't accurate. This is just me giving you an example. So 4 bits per pixel, sorry, 2 bits per pixel could give us 4 colors. So imagine if we went to 3 bits. 3 bits gives us 8 potential colors we can use. The higher the bit quality, the more colors we can store. The more colors we can store, the better the quality of the image. The better the quality of the image, the more or the higher the file size. So file size goes up based upon, and quality goes up. So what we need to look at now is how images are stored. So we looked at how they're represented, but stored on a computer. Let's do a calculation. We've got to calculate the size of this image, the file size. So how can we do that? We need some information. We need to know the height. So let's imagine that the height was 20 pixels. And let's imagine the width was also 20 pixels. We would get height multiplied by the width multiplied by the bits per pixel. So let's imagine that this picture was using 2 colors only. In fact, let's do that. So here we go, 2 bits per pixel. So it's a basic picture, 2 bits per pixel. Quality is going to be naff, really bad, because we're not using that many colors. So if we want to work out the file size, we've got our 20 height, 20 width, times 2 bits per pixel. Now, it's going to give us our answer in bits. So we know that it's going to be, if we do this calculation, 800 bits. That's the file size. But what happens if I want it in bytes? So, remember, you've got bits at the bottom, nibble, but we can skip nibble, bytes. How do we get it from bits to bytes? Well, we divide it by 8, remember. 8 bits in a byte. So we need to take this 800 and divide it by 8. This gives us 100 bytes. So we've just calculated the file size of this image by taking the width, the height, the bits per pixel. It gave us our answer as bits. We now turned it into bytes. If we wanted to turn it to kilobytes, we'd then divide it by 1024. But we're not going to do that. So let's do another example. Okay, so let's imagine that we've got an image which is 25 by 50. And instead of me telling you how many bits per pixel, I'm going to say it's using 8 colors. Give me the answer in bits. What would you have to do to give me the answer in bits? Pause the video, give it a go yourself first. Okay, well, you'll have to do 50 multiplied by 25. Multiplied by not 8, but we need to know how many bits that is. Yes, you can use this table. 8 colors, 3 bits per pixel, but you need to be able to do it without that table. Here's a trick. Let's start off with 2 bits per pixel. I'm going to do 2 bits. I'm going to do a 1 here, a 1 here. So we've got, if I add these 2 up, it gives us 3. But I'm also going to add a bonus 1 here. So now we've got 4. 2 bits of pixels, 2 bits per pixel equals 4 colors. You might be like, what? Let me do another one. And if you look at the table, it matches up. Let's do 4 bits per pixel. So 1, 2, 4, 8. 1 plus 1 plus 1 plus 1, that gives you 15, plus a bonus 1 equals 16. So I know that 4 bits per pixel is 16. So if I'm saying we're using 8 colors, 1, 2, 4, 1 plus 1 plus 1 gives us 7, plus the bonus 1 I keep talking about gives us 8. So we have 3 bits per pixel to give us 8 colors. So the answer there is 3. 50 times 25 times gives us 3750 bits. Happy days. Let me give you another challenge. But this time I'm going to get rid of the table. Let's say we've got 10 by 10 and we're using 2 bits per pixel. Calculate that for me. Pause the video. So that should be 10 multiplied by 10 multiplied by 2 because we've already got it in our bits. So that would be 200 bits. Let me give you another one. 5, 5, and we're using, let's say, 16 colors. calculate the image file size. So it should be, pause the video, give it a go yourself first. Okay, 5 times 5 times, what is 16 colors? Well, if I do 1, 2, 4, 8, and we do 1 bit, 2 bit, so that gives us 12, 14, 15 plus 1, but we don't include that in the counting. We've got 1, 2, 3, 4. 4 bits per pixel, so 5 times 5 times 4. 5 times 5 times 4 is 100. If we want to turn that into bytes, we need to then divide that by 8. 100 divided by 8, 12.5 bytes. So let's have a look at how sound is represented. We've got two different sound waves going on here. Notice some different terminology. We've got sample rate and this aspect called bit depth. Don't worry about amplitude per se, just bit depth and sample rate. Another name for bit depth I'm going to be using is resolution, which I can't spell. There you go. So what's this representing in itself? Well, these sample rates, which are the blue bars here that we see on both sides, is a sample which is taken. They are called sample points. So this is a sample point. Well, I'm drawing it as a sample point. A sample point. The sample rate, which are basically the amount of sample points we have, is how many times per second we record and we capture that sound. Simple as that. The more sample points we have, the higher our sample rate, the higher the sample rate, the more of the sounds we are going to record and store in our computer. If I was to decide, this is my sound, and I'm going to put a sample point here, and here, and here, and here, and here, you'll see there's not many sample points, so the sample rate will be low. That means the quality of my sound will suck. But file size will be quite small, but quality will also be down. So FS for file size, Q for quality. The more sample points we have, the higher the sample rate, the higher the sample rate, the more the sound which is being stored. So the more points we have, the more accurate it is to the original sound. So that's one important detail when it comes to storing sound. The amount of sample points, i.e. the sample rate. Now, not just that. What else do we need to take into account? The bit depth or the resolution. Have a look at the difference between image 1 and image 2. What do you notice about the lines between them? Well, these horizontal lines represent the possible levels that can be used to measure the amplitude. In this 8-bit version, we can see that there are fewer lines, fewer levels. That basically means that sound can only be recorded at that level. That basically means that's going to be a lower quality of sound. We've got less options to record our sound on. Why is that? So let me give you an analogy for this to begin with. Think of bit depth like the number of crayons you've got in a box. So we've got a red crayon, we've got a yellow crayon, and we've got a green one. If we've only got a few crayons like this to draw a picture, or should we say, yeah, a few crayons to draw this picture, we've got a low bit depth. or resolution. That means that our picture isn't going to be that realistic, but if we've got more crayons of loads and thousands of different shades, we'll have a higher bit depth, which means our image will be more detailed, more vibrant. Let's go with that, more detailed. So higher the bit depth, more detailed. So in terms of sound, the bit depth tells us how many different levels of volume we can have and we can capture. This means that we can record all levels of loudness, from a whisper to a loud noise. So if we're watching a movie, we want to ensure that we have the highest bit depth, because in movies, like a horror movie, you might have someone breathing really lightly. You might not be able to pick that up if you lower the bit depth, because it'll just get rid of it. They call that background noise. If you're recording a song, you've got to be careful, because you might have some background noise you might not want in a studio. But you still want a good quality bit depth, because you want to pick up the range of a singer's sound. Does that make sense? Because you want to pick up a pitch to the most accurate level. So the bit depth is all about the richness of the recording. The sample rate is all about what points of the song or sound we are going to store. Together, that is how sound is stored. But we also need to know it through calculations. So how can we calculate the file size of sound? We need to take into account a couple of things. The file size equals sample rate. So we know what sample rate is, multiplied by the bit depth or sample resolution. Multiplied by the length of the sound. So taking into account all those things for now, I might add an extra thing to this in a second, we should be able to calculate the file size of a song. So let's imagine our sample rate, which is measured in kilohertz, by the way. So sample rate is measured in kilohertz. Kilohertz, we take the number and we multiply it by 1,000. So if we've got 4 kilohertz, it'll be 4,000, which we need to use in our calculation, because we're going to be turning it into bits. So let's take a sample rate of 8 kilohertz multiplied by 16 bits multiplied by 30 seconds. All we have to do is turn the kilohertz into bits, so that'll be 8,000 multiplied by 16, because it's already in bits, multiplied by 30. That will give 384000 bits. I think that's 4 zeros. Yep. And then if we have to turn this into bytes, we know what we're going to do. We're going to divide it by 8, so that'll give us 48000 bytes. And to kilobytes, divide by 1024, 468.75 kilobytes. Happy days. Let's try a different one. What happens if we were to have a sample rate of 1 kilohertz, sample resolution of, let's say, 8 bits, and the length 1 second. Calculate that. Pause the video. Okay, so we know that we're going to turn this into 1,000 times 8, which gives us 8,000 times 1, which is still 8,000, so 8,000 bits. To turn that into bytes, we divide it by 8, which gives us 1,000 bytes. You can also divide it by 1024 to get into kilobytes, but I'm not going to do that now. So remember, the kilohertz, you've got to multiply it by 1,000. They could also throw in speakers as well. Let me explain. You could have different types of speakers. So I've added right now different speakers, or we're going to use the word channels. This is called mono. You've got like one speaker with sound coming out one way. So we call that one channel of sound. We've then got what we call stereo. That is two different channels. You then have surround sound. In this situation, you've got one speaker, two speaker, three, four. So that is 4 channels for the surround sound. Now for GCSE Computer Science, you need to be potentially aware of the channels. For digital technology, you don't at A-level. So, but it's still worth knowing. And I think I've just gone off the screen. There we go. All right. So all you have to do is then multiply it by the channels as well. So if we were to have a sample rate of 1 kilohertz, sample resolution of 1 bit, length of 1 second, but coming out of stereo, our formula would be 1 times 1 times 1. Actually, sorry, it would be 1,000. I've got to convert that into 1,000 times 1 times 1 times 2. So 2,000 bits. So all we do with the channels is just add that into the multiplication.